So welcome everyone to the Spectral Geometry in the Cloud seminar. Today we have the pleasure of having James Kennedy, who will speak about spectral minimal partitions of metric graph, what and why. Please go ahead.
Great. Thank you very much. Thank you very much for the invitation to be here. It is a pleasure. And actually, to begin with, thank you for doing this service to the whole community. I think we all know that these webinars are kind of a reference for the shape optimization spectral geometry community. So it is a pleasure to have the opportunity to speak and to present this work. So today I'll be talking about a collection of related projects on, I guess the title kind of says it all. My background is really in sort of shape optimization spectral theory. About a decade ago, a colleague of mine at the time, Delio Mugnolo, who I believe is due to present next week, got me interested in the world of metric graphs, which have... at first, I was skeptical because they're basically sort of one-dimensional objects, so you don't expect to be able to get very much out of them. But, and this is kind of one of the lessons or one of the messages I'm trying to sell today. As it turns out, they sort of do display very rich spectral behavior, and they can also be really nice sandboxes to sort of test hypotheses and sort of see what kinds of things you should expect to happen on domains and manifolds. So I'll be presenting essentially two different new results that we have on graphs for, well, as you can guess from the title, spectral minimal partitions, but they're problems where previously people didn't really think about them at all on domains, and where it very much looks like interesting things will happen on domains. And we're now sort of work in progress trying to prove that these things happen on domains, but sort of the whole thing started on graphs. But anyway, to go back to the start, just a brief reminder, I think in this community this should be fairly well known, but just sort of to set the stage, when I talk about spectral minimal partitions, so I mean the default problem here, take a bounded sufficiently regular domain in 2D, you want to partition it into some fixed number k pieces, and you want to build some kind of functional based on the eigenvalues of those pieces, and then you want to minimize or maximize the functional. So the prototype case, you imagine the first eigenvalue of the Dirichlet Laplacian, you calculate that on each eigenvalue, you look at the maximum of these however many k eigenvalues, or potentially some other p sum, some weighted sum or something. And the goal, the problem, is to find a partition realizing among all possible partitions the minimal value of this function. And well, I mean, the first basic question is whether this problem is well posed, whether there exist minima. And sort of this is something that's now got about 20 plus years of history to it. To me, it's kind of telling that this problem was probably first studied most intensively by the Italian school of sort of doing calculus of variations, which is to say that they're doing really sort of, they look at some weak formulation of this problem, possibly involving systems or something, and they then do the usual calculus of variations analysis to prove existence in some weak framework and then study regularity. But it's sort of possibly better known in this community for the work of others from sort of mathematical physics coming a bit later, who established a whole bunch of connections to spectral properties of the Laplacian on the whole domain. And, well, these are things I think we've seen in previous talks not that long ago, but just to recap, one of the main reasons they're interesting to the community is the link to so-called nodal partitions, where you look at sort of a Laplacian eigenfunction on the whole domain that has some number less than or equal to k connected components of the set where it's different from zero, call each one of them a nodal domain. Well, how many does it have? This is a classical problem from the 20th century. What kinds of properties do they have? I mean, there are basic fundamental open questions here to study the so-called nodal count of kth eigenvalue, eigenfunction as k becomes large. But so it's sort of now well known, at least under decent basic conditions on the domain. Analytic domain, simply connected 2 dimensions, you can do better. But to simplify, your eigenfunction has the maximal possible number k of nodal domains if and only if that realizes a k-partition, which is to say a minimal partition, which is to say that your kth eigenvalue is then equal to the minimal energy of this function. And this, of course, is a very deep connection because you're looking at 2 fundamentally different problems. And this is something that was sort of studied a lot in the 2010s, including by a number of people who are quite possibly in the audience. So I won't be talking about this, but this is sort of a big topic of recent interest. More recently, in the last 5 years or so, because then that begs the question, what happens for other cases? What happens if you have fewer than k, strictly connected components? What can you say? And curiously enough, also coming from the world of metric graphs, sort of a community has started looking at so-called nodal deficiency and spectral flows, characterizing sort of the difference between the number of nodal domains that an eigenfunction actually has and sort of the maximum number of possible k in terms of Morse index of Hessians of well-defined operators that have to do with Dirichlet Neumann maps and things like that. I think you've had talks on this quite not that long ago in the webinar. So this is also something I won't be talking about, but just for future reference. Spectral minimal partitions, you expect deep connections to the operator on the whole domain. And, well, the thing I'm trying to sell today, metric graphs, can actually be useful to give us an idea of what to expect. We've kind of already seen that in this context. But the other kind of problem, I guess the other class of problems or applications that are going to come up today a bit are essentially the geometric interpretation of these. The idea that's sort of common in a lot of discrete analysis, where you have a data set, a discrete graph or something, and you want to look for clusters. You want to look for regions which are highly connected within themselves, or with few connections sort of between one region and the others. And so this is also at the base of a certain amount of machine learning. One approach that was originally pioneered on manifolds, which again, I'm kind of preaching to the choir here, sort of Cheeger's approach of let's look and see whether we can how cheaply we can cut a manifold or something into 2 pieces of roughly the same size. You take this sort of isoperimetric ratio on each, and you imagine the boundary not really as being necessarily the boundary of the whole object, but imagine this as a manifold without boundary. It's sort of the boundary of the cut set. You look at sort of prototypically 2, you could cut into more than 2 pieces. You look at the worst of these isoperimetric ratios and you try and make it as small as possible. So if you have some kind of dumbbell-shaped object, that will have a small Cheeger quotient here, that this infimum will be small. If you have something tightly connected, like a sort of a sphere or something, it'll be a lot larger. And what's possibly less well known to a lot of people, this is also something that one does a fair bit on graphs, on discrete graphs, where you really just sort of have vertices connected by relations. You sort of count how many relations you have to cut, divided by the volume, which is the number of vertices on each side. And this is something people do a lot. The problem is finding these things. This does have a variational characterization, but it's not a good one. So calculating these things is hard. My understanding is on discrete graphs, it's actually an NP-hard problem. And so one can often use eigenvalue problems as proxies. One of the most obvious ones, you look at the P Laplacian. Its first eigenvalue sort of has the same characterization as the Laplacian, and just you replace 2 with P. So you cut into 2 pieces. It's kind of well known in that case. You sort of, the first non-trivial eigenfunction, which still exists for the P Laplacian, sort of the first sign-changing one, cuts the region into exactly 2 pieces, and those represent an optimal 2 partition in a fairly strong sense. And as P converges to 1, this is known as sort of classic in sort of calculus variations PDEs to converge to the corresponding Cheeger quotient. And so basically you can, what you do, you could do this for p equals 2, for k equals 2 for 2 pieces at least. What do you do in general? I mean, P Laplacian being a nonlinear operator isn't great for eigenvalue, k eigenvalues in general. You can look at the linear problem. Of course, then you have the problem that, well, the kth eigenfunction doesn't cut your domain into k pieces. So you want some kind of proxy. One potential proxy that I think hasn't been explored as much as it could be is spectral minimal partitions, especially p versions of spectral minimal partitions. But at any rate, just to point out that there are these, I think, also quite deep connections between geometric objects, this sort of Cheeger cut, which is really a purely geometric quantity, and sort of eigenvalue problems, minimization for functionals of eigenvalues and that sort of thing. And both of these things are going to come up, if I don't go too slowly, by the end of the talk. So I'd like to switch tracks slightly and start talking about what spectral minimal partitions look like on metric graphs. Now, we've had a few talks on metric graphs in the past. I think there's something that for a lot of people still aren't all that interesting and or are a bit exotic. If you like, to me, the way that I think of them is kind of one-dimensional manifolds with singularities, or at least locally the kind of one-dimensional manifolds with singularities. So formally, I'm taking a connected graph. I don't care if it has parallel edges, sort of multiple edges between two vertices. I don't care if it has loops. For the meantime, just assume that it's compact, which is to say a finite vertex set, a finite edge set, all edges have finite length. What do I mean by that? Well, we identify each edge with an interval. More precisely, imagine putting sort of on each edge local coordinates. I cut out a piece of an interval 0 to L and sort of identified coordinate charts, whatever. On the edge, I parameterize functions by saying 0 to L. It's easy to construct a metric space out of this because each interval by itself is a metric space, obviously. And if I imagine the vertices as being glued together, I can easily define the distance between 2 points, say one here and one here, by looking at all possible paths between them, sort of images of continuous functions, being that this sort of has to run through the vertices, and look at the minimal possible length. Sort of this plus this would give me the minimal length, and that gives me a metric space. I mean, I can equally do it exactly at the level of functions by saying that a function is continuous if and only if it's continuous on each edge and sort of on each vertex at all of the endpoints that I glue together to form that vertex, it takes the same value. And this is completely equivalent. So they're sort of, regardless of how we define them, they're fairly canonical objects. But of course, we're going to be doing analysis. One of the easiest ways to do analysis, one of the most important things that we need to do sort of PDEs and analysis is, of course, Sobolev spaces. And this is one of the points, of course, where these objects have an advantage because being one-dimensional, all functions, H1 functions are automatically continuous. So they're continuous on each edge. The natural way to define a space of continuous functions on the whole graph, a space of H1 functions on the whole graph, well, they should be continuous on the whole graph and they should be H1 on each edge. Point evaluations make sense. I have well-defined values on the vertices and, everything agrees. So they can basically have kinks at the vertices, but they're still continuous. That is a canonical definition that works for everything that we want to do. Higher order Sobolev spaces are highly problematic because there's no natural analog for higher order derivatives at the vertices. Now, the other thing, of course, if we're going to be talking about subgraphs or subsets, partitions, we do need subgraphs. So, I mean, imagine just sort of taking a set like this. Now, again, think of these as being manifolds, which is to say when we start talking about boundaries of these sets, the boundary should really be just the points where the topological boundary where it intersects the rest of the domain, the rest of the graph. These endpoints do not count as boundary because they're from the point of view of the manifold, they're in the middle of the set. For certain other purposes, you may want to put sort of measurements here and treat it as a boundary. For us, boundary is really just what's happening in the interior. Think of manifolds. Okay, well, I mean, how do you define a partition? That's fairly obvious. You take a bunch of subgraphs. They should be pairwise disjoint. For technical reasons, I'm going to assume that they're closed, which means that they're allowed to overlap at the vertices. I'm also going to assume they're connected because connected makes sense. So in this particular case, this partition has 3 pieces, 3 components, and exactly 2 boundary points, one here and one here. And so, I mean, what does one do? Well, one can try doing exactly the same thing as before. One puts sort of a Dirichlet eigenvalue in each piece. And these, if I have at least one boundary point, it's a very easy exercise to show that my Rayleigh quotient, the infimum, is, I really do have a Friedrichs inequality. I have a strictly positive eigenvalue. And I do exactly the same thing as before. Prototype, I take the maximum of these things, and I want to minimize that over all possible choices of k-partitions or some fixed k. Well, what's the point of doing this? It's a game we can play. What do we get out of it? As I keep saying, and really the message I want to hammer home, these things will actually turn out to be useful for getting intuition on some things. And I think sort of nodal deficiency spectral flows is already a good example of that. I hope to convince you that there are others. You can sort of say a lot more than you can on domains. And sort of works of Ramban, Gregory Berkolaiko, Uzi Smolansky, sort of beginning over a decade ago, before we had a well-developed sort of existence theory for these things. If you want to analyze nodal domains and nodal counts, metric graphs offer a much richer setting where you can say a lot more than on domains. You tend to have a nodal deficit, but the nodal deficit is finite, at least sort of under some genericity assumptions. So you can say a lot about nodal statistics that you can't on domains, or at least that are sort of well beyond our capacity to with the state of the art these days, to say on domains. And as mentioned, they also sort of give insights into phenomena that we then observe on domains. Magnetic Laplacians are also an example of this. But one of the things to me, sort of with some co-authors, we developed admittedly not entirely satisfactory existence theory a few years ago. Basically, existence and regularity are far less problematic than they are on domains. So you can kind of stop worrying about whether your problem is well posed and sort of start asking what properties does it have far more rapidly. And first question, why is this so? First observation, one of the key points, the boundary is zero-dimensional. The boundary is a finite set. So basically, I can up to sort of topology, up to wiggling around where the boundary points are, there are only finitely many ways that my sort of finitely many topological configurations for any given k-partition. Basically, I just have to look at how many boundary points per edge, and sort of then that will divide into a certain number of pieces, and yeah, that's it. And so within each piece, if I look at 2 partitions which are topologically have the same configuration, this is an equivalence class. So what do I mean by that? Again, just imagine this point. If I move this boundary point along the edge, I've got a homeomorphism between all of my pieces. I have an equivalence class. This point is a bit more problematic. We'll get back to that. But so what that means, if I take some kind of functional, a minimizing sequence, up to a subsequence, all of my minimizing partitions in this sequence have the same topological configuration because there are only finitely many possibilities. And that means up to a subsequence, basically all that's happening, these points are wiggling around a little bit. And that means as long as my functional is at least lower semi-continuous with respect to shifting this point around, I can reasonably hope that sort of that there will actually be a minimizer, that I will converge to something. So basically all I need is continuity plus a couple of technical features. So first point, I mean, if I have a sequence of k-partitions and I'm converging to a minimum, I want the limit really to be a k-partition. So that means in the limit, I don't want any piece to be disappearing, a point sort of drifting from here down towards this edge. That requires some kind of property, prototypically coercivity, that says that if a piece gets too small, my functional explodes. The other thing, of course, is that vertices, one has to be a bit careful because one can kind of approach vertices from various different ways. And a lot of functionals in practice may or may not actually be continuous at the vertices. That requires a bit of careful analysis, but even still, it's a lot less heavy than what we would have to do on domains. So basically just compactness and looking at things the right way, you get existence for all minimizers or maximizers of a large class of functions. So to give an example, look at the equivalent of the Neumann Laplacian. The first eigenvalue is 0. The second eigenvalue, the spectral gap, is, well, assuming the object is connected, is strictly positive. You also think of this, I mean, if you prefer, think of this as Laplace-Beltrami rather than Neumann. If you look at, instead of taking the first Dirichlet eigenvalue, you take this sort of first non-trivial Neumann equivalent eigenvalue, you can get optimal partitions, and not just for sort of minimizing the maximum, you could also maximize the minimum, and that will lead to well-defined problems. Whether they're interesting, we still don't know, but these are certainly things that you could never do on domains. On domains, you try and minimize Neumann eigenvalues, you're certainly going to get dumbbell things that just sort of their eigenvalue converges to 0 at the limit. And again, the other point that I want to make, and these are the two concrete examples I'll be talking about for the remaining 30-something minutes. Two examples where we have nice results on graphs that we're now trying to translate to domains. So firstly, what happens if your object is unbounded, which is to say infinite volume? Do spectral minimal partitions still make sense? Obviously, the answer is going to be yes, but sort of what happens? And the second one, what happens if you look, instead of sort of Neumann, if you look at Robin eigenvalues? And this is an interesting problem because, and I like it a lot, partly because it shows links to Cheeger, the Cheeger constants that we saw earlier, which sort of was unexpected when we first came across it. So the first part will be joint work with Matthias Hofmann, who's currently at Texas A&M, and Andreas Serio, who was a student in Stockholm who's sort of now left academia. And Robin problem was joint work with a colleague in Lisbon, João Pedro Bay. So yeah, what happens if we have an infinite object? Can we still guarantee existence of minimizers? What kind of behavior do we expect for these infimal values? For domains, for bounded domains, these somehow represent analogs of eigenvalues. You could still ask questions like via asymptotics. What can we say here? And can we relate these partitions somehow to the eigenvalues of the operator on the whole thing? Because the graph is a domain, is basically a manifold without boundary, the operator on the whole thing won't be the Dirichlet Laplacian, because we don't have boundary. It will be this standard Laplacian, which is to say the equivalent of the Laplace-Beltrami operator. So I'm once again going to preach to the choir on this, but just to recall what the spectrum of a sort of an unbounded domain could look like for Laplace-type operators, which equally applies to graphs. And because of the interesting geometry of graphs, you can kind of generate interesting spectral behavior even without having to add a potential. We will, however, be adding a potential just to broaden the classes. So, I mean, imagine you have, if you think about it, if you prefer to think about domains, you have a domain, you lay a potential across the domain. This sort of represents areas that are energetically attractive, where the potential has a well, and energetically very unattractive, where the potential is large. And sort of with this underlying landscape, you want to ask sort of what's the best way to cut your domain up into k pieces. So as happens on domains, if you have infinite total length, you can actually, it is actually possible, but there are special examples somehow where the form domain nevertheless compactly embeds in L2. In general, it won't. So you will have sort of more than just a discrete spectrum. You will tend to have some infimum of the essential spectrum. You may get bands. So this picture may potentially be misleading. You may really have sort of bands and gaps. But there will, of course, be a well-defined infimum. Could be infinity if you have discrete spectrum. And the eigenvalues, there may be eigenvalues below the essential spectrum. If there are, they're characterized by the usual min-max principles, and they accumulate, well, they're either finite in number or they accumulate at sigma. And we're going to see that spectral minimal partitions do something similar. So we're going to look at the Dirichlet problem, which is to say, once again, you look at zero boundary conditions exactly where your subgraph sort of has its topological boundary where it intersects with the other subgraphs, which is to say, if all goes well, these could be nodal domains of an eigenfunction that exists on the whole graph. And so we do this for any subgraph. We sort of keep the potential restricted to that subgraph. And this infimum, well, there are two possibilities. It's either an isolated eigenvalue or it's the infimum of the essential spectrum on omega, which is at least as large as the infimum of the essential spectrum on the larger graph, simply by domain monotonicity. And so as before we play the usual game, we sort of look at the first eigenvalue or the infimum of the spectrum on each. We construct a functional maximizing that, and we ask, when do we have a minimum? And so, well, the theorem. So firstly, and this is the easy part, if you think about it for a couple of minutes, this spectral optimal energy can never exceed the infimum of the essential spectrum. More than that, you have something that recalls a test function principle for domains. If the infimal energy is strictly less than your threshold, then you have existence. Then you really have sort of, you can divide the graph into k regions connected, and on each region, sort of, you will get a ground state. So not only will you have sort of existence, you'll have k ground states. And above that, well, it's not quite clear what the right problems are, but sort of unlike with the spectral gaps and bands, for any lambda above the threshold, you could always get an infinite equipartition, sort of spectral equipartition, where the first, well, the infimum of the spectrum is always equal to your predefined lambda. So this is a bit less interesting, I guess. For me, the really interesting thing is point number 2. And in particular, because obviously determining the infimum is not easy in general, but what you do, you take a test partition. If you have a test partition with energy no bigger than sigma, I mean, if it's equal to sigma, that also works because there are two possibilities. Either the infimum is less, or if the infimum is equal to sigma, your test partition is already but I would really like to draw attention to the parallels with sort of the actual spectrum of the whole graph or domain. If you can find test functions whose Rayleigh quotient is less than sigma, sort of a k-dimensional space, then you know you have at least k eigenvalues. So this is really essentially the same principle. Now, if we're restricting to connected graphs, subgraphs, as seems natural, to give a few simple examples, this condition is essentially optimal. So simplestly, you can imagine the free Laplacian on R, it's spectrum is 0 infinity. You can find a minimizing partition for one piece, just the whole thing, 2 pieces, 2 half lines. Note that you don't have ground states. But for 3 or above, you cannot find 3 connected components, precisely because, in the middle, you always have to put a piece of finite length. And you can converge to the limit 0 simply by making omega 2 bigger and bigger and bigger. You'll never get down to 0. So really, this sort of less than sigma condition is kind of optimal. And if you have equal to sigma, basically anything and everything can happen. Possibly almost less interesting example, quantum harmonic oscillator. You'll be able to divide it. I haven't bothered trying to divide this up. This is an exercise I'd give to students who are either interested or I don't like them very much, for them to calculate. But we know it will exist. It wouldn't be hard. They're obviously going to congregate in the middle and then sort of get bigger and bigger as you push outwards the components. Slightly more interesting, imagine cutting that off. The infimum of the essential spectrum becomes the level C at which you cut off. Depending on the relationship between depending on C and K, I guess, you may manage to get a finite number of pieces living in the well that you get there. For K large enough, I'm pretty sure you'll no longer have existence. You'll get back to C. Now, there are quite a few technicalities in the proof, but the underlying idea is not that difficult, at least to the idea of why it's always no bigger than sigma. And this has to do with, this is also one of the reasons why this should work on domains and why we're now trying to get it to work on domains. basically what is the sigma, what is the infimum of the essential spectrum, Pearson's theorem, and this is possibly less well known to some people. Hi, Evans. If you think of a domain, that may be easier than a graph, but it doesn't matter. You cut out a large ball. You look at the first eigenvalue of the complement of the large ball with sort of Dirichlet boundary conditions. As you push the ball outwards, domain monotonicity means that this value keeps getting higher and higher and higher. Now, it's always at least as large as the infimum of the spectrum by domain monotonicity. In the limit, as sort of your ball expands outwards, this sort of infimum of what remains converges from below to the infimum of the essential spectrum. It's kind of what the domain's doing at infinity in my sense, and sort of this is a limit. It's a supremum because of domain monotonicity. And sort of what you can do for any lambda strictly bigger than sigma, it's easy to construct a test partition, and this works equally on domains or graphs. I've got a map. Now I've only been to London a couple of times. Technically, the graph that's here is a finite graph, but my experience when taking the underground was that it certainly felt infinite. It seemed like it went on forever. But so this is the sort of kind of graph we're talking about. Well, no, again, if it kept going on forever. Imagine sort of you start in the middle, you sort of expand outwards until you reach a certain value, lambda bigger than sigma. You then sort of cut off at that value, and then you look at the next ring outwards, and then sort of you expand that ring outwards. If your lambda is strictly bigger than sigma, this principle means that once the ring is fat enough, its energy will drop below your lambda because it's converging to sigma. So you cut off at some point. Lambda, you have to worry a bit about continuity, and then sort of you keep going. You just sort of keep cutting concentric rings of the same value out of your domain or your graph. On graphs, it is a little bit fiddly because you do have to worry about continuity, because you might sort of expand out and then have to contract backwards. I mean, I possibly should have zoomed in on this, but I mean, you can see in this particular case, you can sort of have isolated bits of your graph that are just sticking into rings that sort of mean that you get sort of a little bit that as you expand the ring, you kind of might get singularities, you might get lower semi-continuity, but not continuity. You could get a bit of an edge that sort of leaves a ring and then goes back in. Sort of everything's possible. For the record, what I should have said, it's written on the slide. It doesn't, as with domains, it doesn't matter where you place your origin. You just sort of take any point in the graph, and then you just expand outwards, and balls, of course, are defined in terms of your standard Euclidean metric. So you're really just sort of looking at all the points of distance no more than r from your given center. And I mean, that's basically all you have to do, and that's why you'll always get this for domains and graphs, or at least you should expect it. The existence is far more subtle. Here, we're really exploiting the one-dimensional nature of these of the graphs. Basically, we're sort of cutting off the graph. We're looking for a minimizer sort of within a ball of fixed radius, which you can always get, and then you kind of use a cutoff argument, use a convergence argument, use a diagonal argument, a whole bunch of subsequences. So as mentioned, this should continue to hold on unbounded domains. It's currently work in progress with colleagues, including a colleague in Lisbon, who's an expert on sort of the calculus variation side of spectral minimal partitions. But obviously, it's sort of a question of finding the right relaxed framework, and then sort of combining the mathematical physics parts with the calculus variations part. Anyway, moving along. So the other class of problems I was wanting to talk about was Robin, spectral minimal partitions with Robin conditions on the boundary, which for me is an object of interest anyway on domains in general. So to recall, I think Robin problems are also something that most people have seen, but are maybe slightly less familiar with than some of the other topics here. So basically, you fix it could theoretically be a function. But to keep things simple, imagine a constant which is going to act as a parameter, alpha, which could be any real or even any complex number theoretically, but to keep things simple, it will be a positive number. And so you imagine same problem as with Neumann, but on the boundary, you put sort of alpha times the trace of the square of the function. On graphs, well, it's the same thing. It looks a little bit different because you have your alpha still, but, well, the boundary is just a discrete set of points. So you put the alpha on all those points, and then you just sort of look at the square of the value of the function on that point, remembering that H1 functions have well-defined values at all points, which is nice. And so this has all the same basic properties for any subgraph, for any reasonable subgraph that it would on domains. So this is sort of basic Kato theory because it's associated with a family of forms which sort of are holomorphic in the sense of Kato. So, I mean, you can imagine it sort of pops directly out of the Rayleigh quotient. As you increase alpha, all of the Rayleigh quotients are increasing for every given function. So this thing is a monotonically increasing function. The first eigenvalue being simple, assuming you're connected, of course, it becomes analytic. And it's always positive. You have basically some kind of a Friedrichs, Poincare type inequality. Alpha equals 0, this term disappears. You recover the standard Laplacian, which is to say sort of Laplace-Beltrami or Neumann. Alpha goes to infinity. As on domains and manifolds, you converge to the Dirichlet eigenvalue because you're basically penalizing the value, the function, the eigenfunction on the boundary more and more until in the limit, it's sort of forced down to 0. But the observation I would like to make, and keeping in mind that this is an analytic function, so it admits in every point a Taylor series expansion. So expanding in alpha equals 0. The 0th term, or the 0th order term, it's just the value it takes on, which is 0. The first order term is alpha times exactly this isoperimetric ratio. And then you get a second order term, which since it's analytic will be alpha squared. So, well, where does this come from? Basically, it's what you get if you plug in the eigenfunction for 0, the constant functions, into the Rayleigh quotient. You get here sort of imagine 1, this gives you 0, this gives you size of the boundary, alpha times size of the boundary, and this gives you volume of the domain. And that's the best, and it makes sense, that's the best first order approximation. You can do this in any point, and in any point, basically the derivative of lambda1 in alpha at any point is sort of the value of the Rayleigh quotient, ignoring the gradient term sort of at the boundary. And it's sort of basically the ratio of the size of the eigenfunction on the boundary to its L2 norm. And this is a well-known formula in the community that works with Robin problems. It holds in sort of basically any setting where this problem makes sense. But okay, so what's going to happen? We define our spectral minimal partition as before. Maximum the eigenvalues on each piece. Again, assume that each of them is sort of a connected graph, subgraph, so we don't have to worry about regularity or anything, which on domains would be a big problem. It's probably not difficult to imagine that the Robin eigenvalue is not as well behaved as Dirichlet, but it has a lot of the same properties. You have lower semi-continuity, which if you sort of shift, if you modify the edge lengths of your graph, which sort of equates to shifting the boundary points of your partition. And it's certainly coercive if because you have a kind of a Poincare type or Pavel Kurasov type inequality. As the size of the graph shrinks to 0, the eigenvalue explodes. So that's all you need to guarantee that there's a minimizer, basically. How do these things depend on alpha? So obviously Cheeger is going to come into this. Let me recall the Cheeger constant, which is to say you look at precisely this, you place the isoperimetric ratio on each of your subgraphs. You look at the biggest of all of them and you try and minimize over all possible partitions. And this gives you sort of a k-Cheeger constant. And the corresponding partition is also known as a Cheeger cut or a k-Cheeger cut. Because again, it's sort of in the discrete graph literature, or in general, this is basically telling you exactly where your highly connected clusters are. So this is really a sort of a way of explicitly identifying the clusters, and the actual partition is more interesting than the value, the energy in this case. But anyway, so our theorem, firstly, and least surprisingly, but again, this is possibly more work than it looks for a number of reasons. As alpha goes to infinity, not only do you have convergence on each fixed domain, or fixed subgraph, you also have convergence of the minimizing energy to its Dirichlet counterpart. As alpha goes to 0, you obviously have to normalize, which does mean this is a singular limit in some sense, but the sort of minimizing value converges to the k-Cheeger constant. And what's in a way more interesting, and well, also very interesting and potentially also very useful, up to a subsequence, you have convergence of the partitions in a natural sense. Convergence of partitions on domains is a little bit harder to talk about, because you'd kind of, I mean, you can talk about Hausdorff distance between sets. That's a little bit difficult because that doesn't align very well with calculus of variations. The best that you can tend to do on domains is something like look at the corresponding eigenfunctions, extend them by 0. This gives you elements of h1 0 of or h1 of Rn, and look at whether these functions are converging. So basically, you have convergence of the supports of the minimizing eigenfunctions in sort of some h1 sense. Here, I really mean you sort of look at the partitions, you compare the corresponding subgraphs that'll sort of be superpositioned, and their boundaries, sort of the Hausdorff distance between them, that the volume of the symmetric difference will really converge to 0. And this both for the Dirichlet partition and for the Cheeger partition. And this, of course, is going to be a consequence of basically sort of compactness and the fact that the sort of partitions, we can kind of stratify the space of partitions into a discrete number of objects, sort of these equivalence classes, each of which has nice compactness properties. Now, I won't go into the proof, merely to say that it is extremely graph-specific. Basically, on graphs, you have a lot of local monotidicity properties and stability properties that on domains are a lot harder. Again, it's the idea that the boundary is zero-dimensional. If I sort of push my points outward just a little bit, I know that the Robin eigenvalue is going to decrease. And this is not true in domains in general. You do not have domain monotidicity. I mean, this is really a local result. You just sort of push it out a little bit, because if you push out enough and you get sort of loops and a different topology happening, things might be more complicated. But no, locally it's enough. And again, the idea is you've got a minimizing sequence of graphs, you kind of, or sort of partitions, you can kind of just find sort of an epsilon. You can find, by expanding by epsilon, you can find an almost partition that covers all of them, that contains all of them, and you can find you can find a partition that's contained in all of them, and this sort of gives you a two-sided stability that you can then use to control what your function is doing. So again, that's the very graph specific. On domains, it's going to be a bit of a pain. Now, there are also a whole bunch of technical issues that I've basically completely suppressed for the unbounded domains. It's really the issue of connectedness. Do you insist that your partition components be connected or not? I mean, imagine if you want a 3-partition of the real line. If you don't insist your partition components be connected, you could basically just sort of cut out bigger and bigger rings, which are sort of just intervals, and sort of glue the interval, or sort of disconnected intervals. Every third interval joined together, and that's omega 1. Every third interval, just call the disjoint union of them omega 2 and omega 3. That gives you a disconnected partition which sort of achieves the minimal energy 0, but it's kind of cheating for multiple reasons. Here, the issue is sort of what to do at vertices. Basically, if I cut through a higher degree vertex, so I mean, imagine you have sort of 2 edges here coming to 2 edges here, and I cut here. I mean, is the size of this vertex 2 or 1? And that's actually a non-trivial question, because depending on how I approximate it, if my graph looks like this, and I'm approximating from this side, I'm kind of approximating by objects that see that as a 1 degree vertex, as a vertex of degree 1. When it hits the boundary, if I then have a vertex of degree 2, I'm going to have problems with lower semi-continuity. But if the graph looks like this, however I cut, sort of whether I cut sort of inside omega and sort of pass, sort of sweeping outwards to meet this vertex, or whether I sort of sweep inwards to meet this vertex, I'll always sort of have size 2. And sort of you think that a vertex like this is highly connected, so somehow it should weigh more if I'm cutting sort of in the graph. And this, just to mention the keywords, has to do with the notion of perimeter that Mazon introduced recently in a couple of works. Basically, you sort of look at the number of vertices in that piece. You look at the number of vertices in the complement of that piece, and you take the minimum. And it turns out that if you do this, this is exactly the perimeter of the piece in the sense that Mazon introduced using functions of total variation. And they were sort of quite comprehensive works of his. They were sort of, well, for me, they were a bit heavy because I couldn't really see what the perimeter was doing on them, because you sort of define it in the usual sense of perimeter in terms of you're sort of minimizing some total variation among all functions of bounded variation, which sort of are equal to 1 on the set, or whose gradient is 1 everywhere on the set. But one can show without too much difficulty that this basically means you're sort of looking at how many vertices are inside, how many vertices are outside, and sort of just do that. Anyway, it's really not important. It's a bit of a sidetrack, but just to say that sort of there are technical things happening here in the background. And so, yeah, for me, the real point is all of this should hold on domains. And this is something we're also now working on with colleagues in Brisbane and Matthias. And the first thing you have to do is deal with existence and deal with regularity theory. And to deal with existence, the first thing you have to do is find the right relaxed setting. And this already exists. Bucur, Fragala, and Giacomini Bucur and Giacomini, in order to generalize the Bossel-Darnez inequality, so the Faber-Crown inequality to the Robin problem on domains with very, very, very weak regularity. They introduced sort of basically what you do. You look at functions of bounded variation, special bounded variation, so their gradients don't have a counterpart, and you then sort of look at their jump set. You model the fact in significantly simpler language. You take the Robin eigenfunction on a domain, you extend it by 0 outside, that has a jump along the boundary. So you measure the size of the jump and you call that part of its gradient. And that gives you a class of functions. They call them SBV, special bounded variation half functions, half because sort of it's the L2 norms that should be that should have finite integrals. And they, curiously enough, about sort of 5 or 6 years ago, proved that for the sum of these eigenvalues, there is a minimizer. They were interested in the honeycomb conjecture, which says that in the limit as k goes to infinity, the minimizers basically should be approaching sort of hexagonal domains, a honeycomb, because, those are the tessellating domains with lowest first eigenvalue. And so they proved this first. I think they've now done it in the Dirichlet case, at least for sums. But they started out by doing it for sums in the Robin case, which also, curiously enough, involves this isoperimetric ratio appearing in the limit. But only for the sum case and only for domains. So this is the right starting point. But then once you have existence in an extremely weak sense, then regularity theory is going to be a huge pain. So sort of once again, the message that I want to drive home here is we've got all of these nice links that sort of appearing on metric graphs, the spectral flows, the link between on these unbounded graphs with the link between the infimum of the essential spectrum and the spectral energies and the partition energies, and here the link between Robin partitions and Cheeger partitions, the Cheeger constant. So, well, that's it basically. These things, even if you're not very interested in them for their own sake, they can often be sort of really useful sandboxes where you get a lot of nice things coming out. So I'm possibly a very, very, very little bit early, but that is really all that I wanted to say. So thank you very much for listening. Thank you very much for coming. That's it.
Thanks a lot, James, for this beautiful talk. We have some time for questions, of course, so you can either unmute yourself or ask them in the chat and we'll relay them to James.
May I start the floor for questions? So
yes, Asma, of course.
Thank you, James, for your talk. So maybe a very naive question. So if you, so all of, so this minimal spectral partition, if you replace partition by subpartition, is the same? Because for Cheeger, higher Cheeger constant, I mean, it's usually easier for subpartition. And the reason that I'm asking is if you want to kind of have domain monotonicity when you deal with the infinite graph, subpartition is always easier. So I don't know.
When you, sorry, dumb question, very naive question back. When you say subpartition, sort of you mean you've already partitioned?
No, subpartition means that the union it's not necessarily the whole set. It's just
right. Yes, sure. I mean, so okay, very good point. And this is an issue that I completely suppressed during my whole talk. The theory, you can do it either way. You can, and I don't think it makes it that much, well, I mean, for our theory, it makes it neither harder nor easier. Basically, okay, it's a little bit harder to prove the abstract existence theorem, but then you have that, so it's not an issue. If your partitions, if your pieces don't exhaust the whole object, you still get existence in the same way. Mm-hmm. And yeah, if you don't have domain monitor, and this is something that we've seen in Neumann, so sort of these standard Laplacian partitions where you sort of take Neumann equivalent eigenvalues. In some cases, you can kind of see that it's better to avoid, in particular, you don't want to form loops. It's better to sort of try and avoid vertices that would give you loops. Mm-hmm. So I mean, really here with there are examples of functionals that we have. It's in this really big, unwieldy paper that, yeah, you get your optimal partitions need not necessarily be exhaustive, may possibly be subpartitions in that sense.
Okay, thank you.
Thank you, Asma, for the question. Do we have other questions for James? So there was something I was wondering through your talk. So somehow this reduction to metric graphs is very suitable to study geometric properties of, say, eigenfunctions and these spectral minimal partitions and all of that. But if they're finite graphs, you expect a finite number of eigenvalues, right? So is there a setting where we can use these graphs to study spectral asymptotics and get a good intuition on that side?
Okay, so careful not to confuse two different worlds here. Discrete graphs, they're the easier in inverted commas object. Because they basically correspond to Laplacian, becomes an n by n matrix if you have n vertices. There you only have a finite number of eigenvalues. The metric graphs, you always have infinite spectrum. Because,
yeah. But I mean, in any way, the question is mostly still, anyways. Is there a way to use the intuition that we get from metric graphs to say something about spectral asymptotics in the
right? That is an extremely delicate question, because the spectral asymptotics on graphs. So the first things that come to mind are Weyl asymptotics and nodal statistics. Mm-hmm. And in both cases, they're really somewhere in between 1D and higher D. The Weyl asymptotics are the same as for an interval, essentially because the boundary, sort of the vertices represent a perturbation of your H1. I mean, imagine an H1 of an interval. You sort of glue together bits and pieces or cut and glue in different ways, and those are the vertices. It's basically, that's a perturbation of finite rank. So you can, and this is one of the weird points, you can only ever shift your eigenvalue count, so your eigenvalues, by a finite rank compared with what you would get on a domain or a union of disconnected domains of the same total length. So the Weyl asymptotics of the first term is exactly the same as for intervals. Nodal statistics are also a bit interesting because you have Courant's theorem. As long as none of your eigenfunctions vanish on the vertices, which is a generic condition in the sense that if you are, for basically almost, if you fix the topology of the graph for almost all choices of edge lengths of your edges in a reasonable sense, this property will hold. And in that case, you have a finite nodal deficiency. And this is work going back to Gregory Berkel-Eichel and co-authors from the 2000s. Basically, you have at most k, your kth eigenfunction has at most k nodal domains, and it has at most k minus first Betti number. Sorry, at least k minus first Betti number, which is to say you lose at most one nodal domain for each independent cycle. And this allows them to do some very interesting nodal statistics. So the only numbers that can come up are sort of k minus 1 down to k minus beta. What's the distribution? And they've discovered recently this converges to some kind of a normal distribution, if I recall correctly, centered around sort of k minus beta over 2. No, I mean, sorry, it's the number halfway between k and beta. It's a symmetric normal distribution. Yeah, and it's not normal. It's it approaches that form anyway.
Okay.
That's bothering me because what I said isn't quite right. But it's sort of they studied a distribution. Pardon me, and yeah.
No, thanks. That makes sense to me. Do we have other questions for the speaker?
I would have a little question, if it's possible.
Yes, of course, Romeo.
You said that it was difficult to define higher order suborder spaces in those graphs, but I would like to know if it's possible, or if it's just difficult, or if it has been made.
Very good question, and nice to meet you, by the way. It is okay. It's maybe difficult is possibly the wrong word. Non-canonical is possibly a better word, because so if you have imagine you have H2, that means your functions are continuous. Your first order derivatives are also continuous up to the endpoints. What do you want your derivatives to do when they meet at the vertex? And the natural thing to assume is the so-called Kirchhoff condition, which is to say that the sum of them should be equal to 0. And sort of this is something I completely brushed over during my talk, but the standard Laplacian that I introduced, this is the condition that the derivatives of the eigenfunctions do actually satisfy. So this is one possibility. You can also demand that all of the derivatives be equal at the vertices, but there are lots of other things you can do. It's sort of, you can sort of impose a Robin condition at the vertices. It's sort of like, unlike with the case of boundary conditions on domains, where you still have the form domain H1 and then it just kind of appears in the form. Here you kind of have to impose the boundary condition when you're defining this. When you're defining the space. So it's sort of the higher up you go, the more choices you have. You can define by Laplacians. And this is something that people have started looking at in the last 5 years or so. But again, then half of the paper, which was quite a very technical half, was to classify all the possible types of vertex conditions that lead to self-adjoint operators, and then what's the space that's associated. So I guess the point is there's no immediate obvious canonical analog of H2 because there's no version of just sort of continuity, or rather. Once again, I should be more careful. imposing that the derivatives be continuous at the vertex is not the right thing to do if you want a natural H2 space.
Okay, thank you.
Yeah. Do we have maybe time for a last question for James? Well, if there are none, let's reconvene next week with a talk again on matrix graphs. So it will be Delio Mugnolo, whose name we see right now on the on this slide, who will be speaking about non-canonical connectivity measures on metric graphs. So see you all next week for this talk.